Okay, so let's take a look at the images formed by a convex lens. I've drawn out the same lens that we looked at in the introduction and noted that its focal distance is 3 centimeters. So I've drawn out a very small tree to be our example object. Now the tree is useful because it's not symmetric in the y direction. So if the orientation of the image changes, we'll note that clearly. And I've also noted that it is 2 centimeters high. If you wanted to analyze the image of an object that was too large to draw on a page, we could always say that this is a scale of 1 meter is 1 centimeter, for example. So this tree would still be small, but a 2-meter tree is probably realistic. Okay. So how do we determine what kind of image we form? There's 2 major strategies here, and we're going to try both of them. The first is ray tracing. With ray tracing, we're going to look at a couple of particularly useful rays from the object passing through the lens. The first one will be very familiar from our introduction. We're going to take a ray of light bouncing off the top of the object and going straight to the lens. We're going to again draw that ray directly to the center of the lens. Okay. And it will be parallel to the optical axis. I'm just going to denote the direction of the light ray. Okay, we know from our general discussion of convex lenses that this ray of light will refract such that it goes through the focal point. Another very useful ray we can draw is going to be very much related to this, in that we're going to go from the top through this focal point and to the center of the lens. Now, in this case, the ray is going to refract such that it becomes parallel to the optical axis. So there's actually a very similar logic here between these 2 rays, because if you consider ray reversibility, you're going to have that first ray going up at an angle through the focal point and then refracting such that it is parallel to the optical axis. There is a third ray, just to be really sure that we draw this correctly, and that's going to be straight through the very center of that lens. And what you've hopefully noticed here is that these 3 rays all intersect at a single point. And this point is going to give us the location of the image, the orientation of the image, and the size of the image. I'm going to go and zoom in here and pick up my original object. And I'm going to bring it over here, and we're going to put it, first of all, upside down, because we can see where the point of convergence is. And the other thing we know is that it's going to shrink. Okay, there we go. So we can also measure that distance away. And so doing this ray tracing, drawing out these light rays, enables us to get the size, orientation, and location of the resulting image, all geometrically without doing any calculation. And it works very well. It works to the extent that your diagram is carefully done and your instruments are accurate to the level that you need. So let's draw out a couple of key measurements. So we're going to have a distance to the original object, and we're going to call that S. So in this case, that S is about 8 centimeters. We already know the height, and now I'm going to draw the distance to the image. And to denote the distance to the object, I used S, which is a more generic distance variable. Then for the distance to the image, I'm going to use S prime. Similarly, I'm going to use H prime when describing the height of the image. Alternatively, you could say, well, HO and HI for the height of the object or the image. And again, I could measure this, and if I did that, I would get 1.2 centimeters. Well, I did, but you couldn't see on the screen. And for a distance away, I get about 4.8 centimeters. But let's take a look at how you can do this precisely. What we're going to use is something called the thin lens equation. So that's going to be 1 over S plus 1 over S prime is equal to 1 over F. So let's try this for this case. If we want to find the distance to the image, we can rearrange this equation to get S prime is equal to SF is over S minus F. So in this case, we have an original distance of 8 centimeters times a focal length of 3 centimeters. And we have now 8 centimeters minus 3 centimeters. Okay, so 8 times 3 is going to be 24, divided by 8 minus 3, which is 5. And so we get 4.8 centimeters. Okay. Now the other thing that we want to know is what is that height? And there's going to be 2 steps here. Step number 1 is to get the magnification factor. And the magnification factor here is going to be M is equal to minus S prime over S. So the ratio of the distances here is going to give us the magnification factor. So the factor difference between the object and the image. Now, let's take a look for this case. S prime is 4.8 centimeters. And S is 8 centimeters. So we get a magnification factor now of minus 0.6. All right. Now you might be wondering, well, why do we have a minus sign there? Well, that is giving us a sense of orientation. So the minus sign is, it's on the other side from the original object, so it's below. Okay, so the next thing that we want to do to work out what the height is to use the magnification factor in order to see what the height ends up being. So it's just going to be the h prime is going to be equal to the magnitude of that m value times the original height. So we get an h prime of 0.6 times 2 centimeters. So h primed is 1.2 centimeters. So if you draw this out for yourself, you can get exactly the same result as if you do the calculation with the thin lens equation. Now, of course, you may notice that, just as an aside here, this magnification factor is also going to be h prime over h. And that's a fairly sensible definition as well. But very often, it just depends on what you are given in the beginning as to which makes sense to use. Okay, so that's an introduction to images with convex lenses. What we see is we can, either through calculation or through ray tracing diagrams, determine what the location, orientation, and scale of that image is. This again will be affected by what the focal length is, and that is determined by the curvature of the lens and what it is made of, or the index of refraction. And of course, where you locate the original object will have a big impact on the size and location of the resulting image. Okay, that's it for now.